So let's say we have a problem called max of 2 times x1 plus 3 times x2, x1 plus 3 times x2 less than or equal to 82.5, and 2.5 x1 plus x2 less than or equal to 8.7. And x1 and x2 are non-negative, and we add for the first time this one. So integer means they take the values of the 0, 1, 2, and so on, right? So that's the meaning of the integer, right? So they are a whole number. Now let's plot this on the Desmos and see what we get, right? So let's plot this. So when we plot this, so I have this problem and I want to plot this constraint. So it's x plus 3y less than or equal to 8.25, 2.5 x plus y is less than or equal to 8.85. So you can by now guess that this is the, because this is a maximization, this is the optimal point, right? You can easily identify this. But this one has an issue, right? So both of these numbers, they are not integer, right? So let's identify the possible integer solutions. So we have 3 and 0, right? We have 3 and 1, right? Then we have here this point, 2 and 2, right? And then 2 and 1, right? Do you all agree so far? So these are the possible solutions that they are. So I can get rid of this. Most likely, this is not the solution, right? So most likely, the solutions that is optimal is one of these points, right? Either this point, which is point 2 and 2, and this one is 2 and 1, or 3 and 1, right? So the possibility is one of this, is most likely one of this. Now, there are ways that we can solve this. For example, I can round these points. For example, if I round this, I'm going to get 3. And then for this one, I'm going to get 2, right? And you can verify from this one that this is not a right way, because 3.3 and 2 is infeasible, right? So we cannot do that. So there might be, for example, I can round them down. For example, this one 2, and then this one 1, right? So I get this point, right? So this rounding is kind of risky, and it is, we are not sure that's going to be the final solution, and so. So in the Excel, there is a method that we call integer programming, and we are gonna discuss in a minute. But this is the structure of the problem, right? So we have some of the variables, some of the decision values are integer, and the name of this one is, in general we call it mixed integer. So M is for mixed. So that means we have some of them are continuous, some of them integer. So this I stands for integer. And we have LP. So mixed integer linear program. So when everything is integer, we call it integer linear program. Okay, makes sense? So either we have I, LP. So everything is integer, but sometimes some of them are integer, some of them are continuous. We call it mixed integer linear program. Okay, makes sense, everyone, so far? Before we had just LP itself. So every variables that we had, it was continuous. Now we are dealing with the situations, some of the variables are integer. Okay? So how we can do this? So the concept behind this is, I just want to explain the basics of it. So it might be a little bit confusing. So don't worry about it because we don't need to do and implement the details. I just want you guys have an understanding of this. So I solved this, right? So this point is my optimal solution. When I apply this in the Excel and get it without enforcing X and Y or X1 and X2 be integers. So we call this LP relaxed. So by relaxed, we mean that we remove the integer constraints, being X and Y be integer. So I solve this, right? So step one, I solve the LP relaxed. Now I get the X and Y values, and I add constraints to the LP relaxation. For example, here I have 2.7, right? So I can cut this by one time saying X should be greater equal 3, right? So one time. So that means I'm gonna have just this area, right? So my feasible area, when I do this, is gonna be this area. Do you agree? So, okay. So this is gonna be my feasible area. Do you all agree? So when I add, so the, so this is gonna be one sub problem or another extension of this LP. So I have a LP plus this one, right? So you remember we had these two constraints. And then we add one more, which is X less than or equal to 2. So I'm breaking down this area. I'm removing this area from the model. Okay? So this is going to be the second problem. So this is going to be number one, right? So this is the number one area feasible area of the number one, and this is the feasible area of the number two, right? Does it make sense so far? So I solved it and then I break down based on the value of the X that you see here. So it is one of them is X less than or equal to 2. One of them is less than or equal to 3, right? So, so this one has both of these constraints plus this one, okay? So both of 1 and 2, they have original constraints plus this extra constraints, right? So I get this. Now I solve this one. So for this one, you can guess this is my optimal solution, right? So for number one. And for this one, this is going to be my optimal solution, right? All right. Then again, because here the X here is, because it is integer, this time I have to cut for the Y. So I add cut to this one. So, or another constraint, for example, I say Y should be greater than 1. So this one is going to be this way, right? Then another one, I'm sorry, Y greater than 2. So this Y greater than 2 is going to be infeasible. There is no such a thing here left, right? Makes sense? One time I have to say Y less than 2, right? Again, this time my optimal solution is going to be this, okay? So this is going to be 3 and 1, okay? So this is one branch of this. I followed one branch of this. So this one end up infeasible. this one end up with optimal solution of 3 and 1. Okay, makes sense? Now I have this area as well. So here you can, one of them is going to be y greater or equal to 4. Another one is going to, I'm sorry, y greater or equal to 2, right? So this area, and you're going to get this as the optimal solution. The other one is going to be y less than or equal 1. So you're going to get this point, I'm sorry, 2 is here. So you're going to get this here, and or this one is here, right? So you get this, you're just adding more constraints and you're making smaller and smaller. So you're going to have another set of the solution here, for example, 2 and 2, okay? So this is the concept that when we apply integer program happens behind the scene, okay? But when we apply in the Excel, this concept is immediately applied and we don't need to be worried about it, okay? Makes sense? So this is called branch and bound, right? So every time you're branching, and then based on the optimal solution, we make some adding constraints, and we don't need to be worried about it. Just something like this is happening behind us. Okay, makes sense, everyone, so far? Is that clear? Okay, so let me show exactly what happens for this specific problem. Okay, so okay, so do you remember we solved this problem, right? So originally we got this, right? So I add these two constraints to the original problem, right? So I'm adding one time x less than or equal 1, less than or equal to 2, and one time greater or equal to 3, because this one is between 2 and 3, right? So one time I'm saying it should be less than or equal to 2, one time greater. So when I solve this, I got this solution. So x1 is equal to 3. Now x2 is equal to this, right? So 1 point. Now, when I solve this side, I got x1 equal to 2 and x1 equal to 2, x2 is 2.8, okay? So the optimal solution of this one is better than this, right? So that means I don't need to follow this anymore, okay? So I cut it, this branch, we stop right here. So we don't continue anymore. Okay, now let's discuss on this branch and what happens. So this branch continues. So here we have x2 equal to 2 and 0.8, right? So I add x2 less than or equal to 2, because this one is between 2 and 3, right? So one time is y less than or equal to 2, one time y greater than 3, right? Okay, so when I do this, this side becomes infeasible. So I cannot go further because it's infeasible. Now, when I do this, I get the x1 equal to 2 and x2 equal to 2, and the solution is both are integers, so it is satisfied. We stop right here. Otherwise, we have to go further and so on, right? Make sense? So this is called branch and bound. So this is example of how branch and bound works, the details, but we don't need to apply and learn it, but I just want to show what happens when we apply this in the Excel. So let's see how we apply it in the Excel. So this is the constraints of this problem, right? So this is the description of this problem. We have maximization of the x1 and x2, and then so here we define x1 and x2. These are my decision variables. My objective function here, so it's going to be the coefficients are 2 and 3. So I calculate the objective function, which is sum product of decision variables, right? So this is now the constraints are 1 and 3. So this is going to be my left-hand side, and both are in the form of less than or equal, and this is right-hand side. And it's 8.25 and 8.75, and it is less than or equal. And the constraints are 2.5 and 1. So this is some product of decision variables time constraints. Okay. Now, to implement this one in the solver, everything is same as the other ones, the linear programs that we have. Just at the end, when you add every constraint, for those decision variables that they are integer, you have to say integer, right? So x1 and x2, they are both integer, right? Makes sense? So this is the only step that says x1 and x2 are the integer one. And when we apply this, the solution is going to be, all right, so let's see where there is. Okay, so here I made mistake. All right. So when we solve this, you can see the solution is exactly same as the one that we got. Okay, makes sense, everyone? So everything is pretty much same as a linear programming in terms of the application, or in terms of implementing this one in the Excel. Just you need to define which variables are integer, right? So that's the only thing that, yeah. Now let's do one example together. So can you solve this one? So, all right, so solve this one in the Excel. So pay attention, the objective function is minimization. All right, so solve this one. All right, so I just want to implement this one, the section B of it, which is the one that has the integer constraints, right? So here I have x1 and x2, and the objective function is 1 and 1, and I just have some product of decision variables times x constraints. Then I have my constraints. So the coefficients are -4 and 4, and it is less than or equal to 2, right? And here I have greater or equal to 15, -8 and 10. So I go to the data solver. So here is my objective function. It is minimization. I select the decision variables, and I add the constraints. And I forgot to calculate my left-hand side. So I'm going to do it in a minute. And then I add my decision variables are integer, right? So here, I'm not going to solve it yet. So I just close it. And then I have the sum product of decision variables times the constraints, coefficients, okay? So when we apply this, when we solve this, okay, so I made some mistakes, I guess. Oh, yeah, thank you. And again, so let me check. Oh, yeah, I forgot just one more. Okay, so this is this is the optimal solution. So that's very interesting to look at the structure of this problem as well. So if you go to the Desmos, you can see -4x plus 4y is less than or equal to 2, minus x plus 10y is greater or equal 50. All right, so you can see this point is the optimal solution when you get rid of those integral constraints, right? So this is the first one. Now look at this when you enforce the optimal integer, you get all the way up to here, right? So from this, we move all the way to this point, right? So that's okay. So that's the difference between removing the integrality constraints and this, okay? Oh, makes sense, everyone? Is that clear? All right. So let's do one more example. So this time, we want to see some of the examples that this can happen in the modeling. Okay, so all right. So this is very good problem. So here we have uh we have 7 shifts that they work 5 days, then they have off for 2 days. For example, those that they work in shift number 1, they have, you know, they take off on Monday and Sunday, right? Make sense? then their wage is $680, and the same thing for the rest of the shifts, right? Shift number 2, 3, 4, and so on. And here we have for Sunday, for example, we need 18 individuals. For Monday, we need 27, and so on. Do you remember we solved exactly same problem like this? Do you recall, guys? You remember the restaurant? You remember? You remember that one? The shifts, 8 hours, and so on. So this is exactly same method. So what would be the decision variable for this one? For each shift, right? So the number of the workers for each shift, right? So you can define xi's. So you can define xi's is the number of employees needed for each shift, right? So I is from 1 to 7. So xi is the number of the individuals we need or number of workers we need for each shift. So the objective function is going to be just the minimizing the costs, right? So 680 times x1 plus 705 times x2 plus the rest, right? Makes sense? So the objective function. Now let's work on the Sunday. So Sunday we need 18 individuals, right? Okay, so how we can find those individuals that they work on Sunday? Can you help me? So this guy or the individuals that they are working on shift number 1, they are not working, right? Do you all agree? At the same time, the same thing happens for this one as well, right? So the summation of the x2 all the way to x6, it should be 18 or more, right? Make sense? Do you agree for Sunday? Okay. So let me, so the objective function is clear, right? So we don't need to write it, right? So let's just hop into the constraints. So the constraints are going to be for Sunday, we are going to have x2 plus all the way to x6. And here you can put equal to 18, but this might end up with the infeasible solution, right? So when you have objective function minimization, you put the constraints, you can put the constraints in the form of the greater equal, okay? Makes sense? But when you have maximization, you can put in the form of the less than, okay? So that's the argument that you can make, okay? So this is for Sunday. Do you all agree? Then you can do for Monday. So who works on Monday? So you can say for on Monday, let me remove all of this. So on Monday, everyone works except X1 and X2, right? Do you all agree? So on Monday, we are going to see X3 to X7, right? So on Monday, X3 plus all the way to X7, we need at least 27. So you guys are confident that we can jump to the Excel now? Is that good enough for you guys? Is that clear enough? So we can implement this one in the Excel? Oh, all right. So help me with this. So I have how many decision variables? I have 7, right? And I have cost associated with each of these 680, 705, 705. 680. 650. So the cost. Thank you. So it is some product of decision variables times this cost. Okay. So I want to write it for Sunday, Monday, all the way to Saturday. And let me write the number of the individuals that I need. So I need 18, 27, 22, 26, 25, 21, 19. So who can work on Sunday? Everyone except, so 1, 1, 1, all the way to X6, right? Do you agree all? And on Monday, everyone works except X1 and X2. Do you all agree? So this is just the shift patterns, right? Do you agree? So I'm not even looking at, so it just, I'm shift every time for each row I'm shifting, and I think it's right. Right? So you can verify for Thursday. For Thursday, X4 and X5, they don't work, the rest work, right? So every time, for every row there is a shift, right? You need, so Saturday, everyone works except the X6 and 7. And here you can calculate the sum product of X size times the these values. You can put equal, but greater equal, because when you put equal, sometimes it might end up with the infeasible solution. So because the objective function is in the form of the minimization, you can change equal to this one. Now let's solve this. So this is my objective function, and I want to minimize the costs. And these are my decision variables when I add my constraints. It is in the form of the greater or equal. And one more thing that I need to add is decision variables are integer. Okay. So when I solve this, here it is on. So you see this here, I have for these 4 of them, the number of the employees are more than this, okay? If I put it equal, this would have caused me issues because it's gonna be infeasible. Okay, so that's the reason that we do it. All right, guys, can you implement this one as well? So you can just, all right, so try to implement this one. a good practice. So far we talked about integers. So integers, they take the values of 0, 1, 2, and so on. We have a subclass of integer. It is called binary, right? So binary, they take the values of 0 and 1. Okay, so they are a subclass of the integer. So this binary is used for example, picking a project or not picking a project, right? So x equal to 1, that means we are working on the project. X equal to 0, we are not picking one. Right? So binary, like. So this is very useful to model constraints, right? For example, I want to pick x1 and x2, but not x3, for example, this kind of constraint. For example, I want to pick at least one of these two projects, for example, right? So when you represent this one, when you want to pick at least x1 and x2, this is the way you represent, right? Makes sense, everyone? So both of the x1 and x2 are binary, and you want to pick at least one of them. This is the way that you represent. For example, you pick x2 if x1 is selected, right? So you pick x2 if x1 is selected, right? Does it make sense, this part? You pick x2 if x1 is selected. That means if x1 is 1, x2 should be 1, right? So when x1 is 1 here, x2 should be 1. But if x1 is 0, x2 could be 0 as well, right? That makes sense. And I'm going to show a bunch of examples of this. Fine. Okay. So the example here is we have a set of the projects that we want to work on this set of the projects. Okay. So I'm sorry, set of the investment. So here we have 6 projects, and here we have the net present values, which we want to maximize this. They need some capital every year for the next 5 years, right? So here for project 1, if we pick it, we have to pay 75,000. Or for project 2, we have to pay 90 and so on. So the same. So here at every year we have some budgets. For example, we have 250, right? Then 75 for the first 2 years, right? And then 50,000 for year 3 and 4, right? So that's the amount of budgets that we have. So 250 at the beginning, for year 275, and so on. And we cannot carry over whatever left from the previous year. So right, makes sense. So whatever we could, we use it, otherwise we don't. So what you think, how would you approach this project if the goal or objective is maximizing the net present value? So what would be your decision variables, given that you have 6 projects and some budget constraints? So you either pick project 1 or not, right? So either you pick project 2 or not. So for each project, you're deciding that, right? So that's called decision variables, right? Do you all agree? So you greater than the expected return. What was the question? So how to decide which one to? Yeah. Then and the real net present values will be equal or greater than the expected. So the goal is here, we wanna get the thing, right? So higher net present value by picking the product. So it's not a matter of, the cost of those projects. Don't think about that. So just, this is a pure hypothetical. Okay, so do you agree Xi for each of this project is a binary variable? Either we pick them or not, right? So that's the two possible case, X1, X2, all the way to X6. Either we pick them or not. So they are binary, right? Okay. Then objective function is just a clear one, right? So maximize 141 times x1 plus 187 x2 and so on. Makes sense? So the objective function is going to be 141 x1 plus 187 x2 all the way to the last one, which is 127 x6, right? Do you all agree? So this is going to be objective function. Its type is maximization, right? So you want to maximize whatever we get, right? Okay. So we address the objective function and decision variables. Now we need to decide on the investment. So for year one, we have 251, right? So if we pick project one, we have to pay 75,000, right? So 75x1 plus, if I pick project two, I'm going to spend $90 on it. 90x2 all the way to last project is 50x6 should be less than or equal the given budget, right? So 250. Does it make sense, everyone? Right. The same thing for the next year. For example, for year five, which is the budget is 50, it is 10 times x1 plus 30 times x2 and all the way to 40 times x6 less than 50. Do you all agree? Okay. All right. So this would, so here is my decision variables. So I decide it is xi's, it is 0 or 1, so they are binary. If I pick the project I, its value is 1, otherwise is 0. Now, this is my objective function. I want to maximize my total net present value. And my constraints are here, right? So in year one, the budget should be less than this one, the given one. Then for year two, year three, and year four. And all of the xi's are binary, okay? So how I decide or how I define binary variables. So it's pretty much same as the integer. Here you just need to check binary. So bin means binary, okay? So that's all. Now you guys, can you implement this model in the Excel? Okay, so I want to see what you get for this one. So first start with objective function. When you are done, I'm going to show you the answer. All right, so this time you solve first. So decision variables are x1 to x6. So the goal is being able to determine the model in 10 minutes. Done with objective function. Guys, so let's do work on the constraint. Okay, so these are the constraints. Anyone got the solution? Now your laptop is getting. That was okay. We'll check them later. future under 10 minutes. Okay, so the goal is being able to. All right, guys. So the meaning of this. So it gives you x2, 1, x. Which one is one? Can you tell me? The solution that we get, one is the value of the x1. What are the values equal to x1? Value or equal to 1. X1, x4, x4. So those are the ones that you pick, and the rest is you don't. Right? So that's the name. Now, these binaries are very useful to modeling, right? So I want to show you some brain teaser. Okay, so don't look at the slides. So, okay, so can you answer this question? You see this at the bottom of project 136, no more than one can be selected. So we want to pick at max one of these projects. How would you model this? At the most, set of people who want. At most means this, right? So that means what? X1 plus X3 plus X6 is less than or equal to 1, right? You see the concept? That makes sense? So at most 1. So that means you have an option to choose none of them, or you can choose either x1. So possible solution for value of the x is all of them are 0, right? So, or the other one is x6 is 0, 1, the rest is 0, or x3 is 1, the rest is 0, or x1 is 1, the rest is 0, right? Does it make sense? So these are the possible solution, and you can see all of those matches this one, the description that we got. All right. Now, how about this? Exactly 1. Equal, right? So here we get rid of less than or equal, we just put it equal, right? So this binary is very useful for modeling. Okay, so how about this? This is very interesting. Project 4 cannot be selected unless project 5 is selected. So I gave so this is very good question, right? So you can so try to come up with a solution for this. How would you come up with any kind of constraint that represent this one? That's basically an answer. Okay, so so the value of the x4 is here and x5 is here, right? So x4, if x5 is 1, x4 should be 1. If it is x5 is 0, this should be 0. So you're saying x4 greater equal x5, right? So that one suggestion. Any other idea, guys? So 4 equal means you can put the equal as well, I guess. Unless, let me see. It when you put equal, so that forces you pick both x4 and x5 at the same time. So you don't put the option that you put x5 without x4. Here, x4 depends on x5, okay? So you can simplify this one as well by shifting them, right? So it was very close, right? Makes sense? It was very close. So let's analyze this, okay? So when x5 is 1, I think this is wrong. So when I think this should be greater or equal. So I think there is a typo. This one is right, right? Because that doesn't show that, right? Do you agree, guys? I think this should be x4 greater or equal x5.
X5 can be selected even if this X4 is not selected.
Yeah. So let me. Oh yeah, this. Let me analyze this, guys. Okay. So this one. So the truth table x4, x5. So when x1 is x5 is 1, x4 could be 0 or 1, right? Do you agree? Using this. So this becomes x4 less than or equal to x5. When x5 is 0, oh yeah, that's right. So when x5 is 0, x4 is absolutely 0. Okay, makes sense? So when x5 is picked up, when we pick the project 5, you have the option to pick or not pick the project 4. So it's not, if you pick 5, you need to pick 4. That's not the interpretation of the question. And there are other one as well. For example, let's jump this one. So this the stuff that I'm not covering is not going to be in any of this. So in any of the upcoming projects. Okay. So this is the last topic that I want to cover today. It is about fixed charge problem, right? So it means like you're doing some production, you have a factory and you want to do some production. So the production like let's say you want to produce something, right? So you need to do some investment to make that production. So if you didn't make that investment, the production is 0, right? Make sense, everyone? So for the production, you need to buy some machines and so on. So if you didn't buy those machines, the production should be zero. So that's the meaning of the fixed charge. So you pay large amount of the money to start the production. Okay, makes sense. So that's called the fixed charge. Now here, let's look at this. So here we have the three products, product 1, 2, and 3. And we have three machines, right? So like machining, grinding, or three operations, right? Machining, grinding, and assembly. And we have profit for each of these and setup cost. So if you want to start producing product 1, you need to have spent $1,000. Unless if you don't spend this, you're not going to be able to produce anything. Okay. So the goal is you want to minimize the cost or maximize the profit. Either way is same, right? So here you either you have a profit here minus cost, or you can say I want to minimize the cost, and both are exactly same. Okay, and so the decision variables, as usual, could be xi is the amount of the product I that we produce, right? That's going to address up to this one. Okay, do you agree? So xi is going to be the amount of the products that we produce, and you can calculate the objective function later. We can. So let me write everything here. Okay, so okay, so xi is the amount of the each product, right? So okay, so the I write objective functions so based so far, and later I'm gonna expand this. So let's write it maximization. So max of the 48 times x1 plus 50 times x2 plus 50 times x3. And the constraints are easy. For example, for the product, for the machining, I have 2x1 plus 3x2 plus 6 times x3 less than or equal to 600. So for machining, and you can write for the grinding and assembly as well, right? Makes sense for the next two. Now, the only thing that I need to answer is how can I include the setup cost, and how to tell if my setup cost, if I do the setup, the production should happen. Okay. All right. Okay, so let's say I introduce another set of the variables that I produce. So if it is 1, so setup happens, setup cost for product I happens. Okay, so that means we decide to produce this product, right? Does it make sense so far? So I need to add minus, because these are the costs, so minus 1000 y1 plus 800 y2 plus 900 y3. So I subtract the setup cost, right? Does it make sense? All right. Now, how can I say if I have, so let's say I want to produce y1. So there is a connection between x1 and y1, right? So if I do some investment on the y1, then x1 should be positive. But if y1 is 0, the value of the x1 should be 0 too, right? So how can I represent that? Can you guys come up with the idea? So the goal is I want to find the relationship between x1 and x2 in such a way that if y1 is 0, x1 should be 0. Otherwise, x1 could be positive. Can you just come up with some ideas? So I want to establish a relationship between x1 and y1. So I want to make sure x1 is 0 if y1 is 0. So here is my goal. So if y1 is 0, x1 should be 0. If y1 is 1, x1 can be any value, any positive value. So I want to establish this one. So one suggestion was you are getting there. So x1 is less than or equal to y1. x1 greater, but when you put y1 equal to 0, then you're forcing it doesn't matter. Okay, so the relationship is other way. So x1 is less than y1, but something is missing here. So if y1 is 1, the maximum amount of the product that I can have is 1, right? So x1 can go. So I put something here. So you remember we just said y1 here, right? So x less than or equal y1. So I put a number called big M. Okay, so this M is like 10,000, 20,000, whatever you want to put, you can put it here. So you are saying that x1 should be less than this one. So you're putting some constraint on that, right? Otherwise, if y1 is 0, then you're putting it, right? Makes sense? So this is called big M. So this is one of the ways that you can establish the relationship between binary and other variables. Make sense? So here you are going to have two more constraints, x2 less than or equal to my2, x3 less than or equal to my3. Okay, so M depends on the type of the problems that you have. For example, you can put 10 million or 10,000, whatever. It depends on the structure of the problem, but it sometimes you have to be very careful what value you are putting for M's because the solvers put weights on the constraints sometimes, depending on the structure of the problem. But it should be somewhere in the range of the problems. For example, here the values of the X here, for example, you can produce 100 units of the X1 based on the available machining. 200 X2, right, and 300 X2. So this 300 seems reasonable value for value of them. Okay, makes sense? I just want to check the assignment and the assignment is We already solved this one, assignment number 1, and this one is exact. So didn't we solve this earlier?
No,
No, we solved this, right?
something else.
So
Oh, no.
so it's similar. So it's, oh yeah, so okay, so this one. So we have the shifts, right? So these are the shifts. The decision variables are defined based on the shifts, right? So X1 is 7 to 11. Okay, wait. So yeah, so these are the shifts. Then, okay, so you define X1 all the way to X whatever here. Okay, so X, I call it 7, whatever it is. 2, 4. Okay, 7, okay. Then for 7 to 11, you need 11, right? So it is greater equal 11. And these two can work on this one, right? So X1 plus X2, right? So it makes sense for this one. Makes sense, everyone? The same thing for 11 to 11 to 1. So these two, they can work, right? So 11 to 1. And so it's going to be X2 plus X3 should be greater or equal 24. And the same for the rest. The only thing that you need to define is the number of the full time and number of, also you have something here. So let me. So here it says at least before and so on. That's okay. So that means the value of the, okay. So X1 and X7 should be greater or equal 1. Okay. So one of them. Then it says at least 30% should be full time during the busy period. So busy period is 11 to 1. So 11 to 1. So who can work on this 11 to 1? It is X1, 11 to 1, right? So X2 plus X, so X2 plus X3 divided by, I'm sorry, X2 divided by this should be greater or equal to 30%. And you can simplify this. Make sense? So, right? So you are making sure 30% of the employees are full-time, right? So is it X2 over X2 plus X3 greater than 0.3? And you linearize it, okay? Makes sense? Yeah, it's a constraint. This should be constraint. Okay, the same thing for the 5 to 7. All right, guys, make sense, everyone? Okay.
Or just those two we have to linear.
Yeah. Everything is same. Everything is, I remember last session we solved something like this or modeled something like this here. Here just, this is a new one. So the 30% should be full-time and so on. Okay. All right. So question number 3. We need to pay attention to this one very, very, very much. Okay. Question number 3. So here we have the 7 places and we have possible sites. So 1, 2, 3, 4, 5. So here, these are the x's, x1, x2, and x5. So this could be 0 or 1, right? So either we place or we build the site here or not, okay? Makes sense? So we want to build some sites that they cover these regions, okay? Make sense? Now here, for the region 1, x1 plus x3 should be greater than 1. So every region should be covered. So here for region 1, I put x1 plus, because of this x's that I have, x3 should be greater or equal 1. The same thing for 2. So it's going to be x1 plus x2 plus x4 and 5, right? Greater than 5. So you want to cover every and each region by one of these sites, okay? And the objective function is a minimizing the cost of it, okay? Makes sense? And xi's are the binary, right? Make sense? Either you build it or you don't. And make sure that you write the model and show your model on the Word document and then solve it, okay? Make sure that you have both of them. So this problem is very important, okay? So this problem number 3 is very important. Number 4, I think is very easy. Okay, so you have 10 applications, 10 possible improvement on the car, and you pick some of them, right? So either you pick it or not. So that means they are binary, and they have some cost. So you want to minimize it, and then here they save the weight of the car. So we want to reduce the weight of the car by at least 400 pounds. So the summation of this weight times xij should be greater than 40, okay? 400, right? Because that's the weight. Change 4 and 7 is alternative. So that means you can pick one of them. So x4 plus x7 less than or equal 1, right? So either one. Only one of them could be selected. That means you can, all right? The rest is pretty much easy. The same thing, question 5 and 3, they are same, guys, okay? I'm sorry. All right. Okay, so here we have, let me read this question. Okay, so you have 6 regions and you can place ambulances in 2 of those, right? So you pick x1 all the way to x6, right? So either is 0 or 1. Okay, so you pick ambulance in region 1, region 2, all the way. Okay. Now, here the distance, so let's first, so if you put in region 1, okay, you can cover region 1, 2, 3, and that's all. Because region 4 and 5, they are more than 4 minutes, right? So that means if you put x1 is, if you put in this one, you're covering region 1, 2, and 3. If you do in 2, you're covering region 1 and 2. The same thing, right? Makes sense? And then you want to increase, or the goal is maximizing the coverage area. All right, so that should be enough, okay? All right, any questions so far, guys? Make sense? Good?